Hi, and welcome to Failurology, a podcast about engineering failures. I'm your host, Nicole.
And I'm Brian, and we're both from Calgary, Alberta, Canada.
Thanks again to our Patreon subscribers. As always, we really appreciate your support.
For the same cost as one used book, not a textbook, but one used romance novel, a couple used romance novels, you can hear us talk about more interesting engineering failures on our Patreon.
Is romance your genre of choice, Brian?
It is not my genre of choice. I watch a lot of Jeopardy. I did not do very well in the romance category from a couple months ago. I think I got 2 clues, 2 answers. So no, it is not my choice.
It's not mine either. I prefer mysteries, which is probably not surprising since these failures are kind of little true life mysteries. I recently went to the used bookstore in town. We have one in Calgary. There are so many books. I'm like a kid in a candy store in there.
What used bookstore did you go to?
Fair's Fair, the one in Inglewood.
Oh yeah. Oh, that's a good one. I spent far too many hours in that store as a kid.
Yeah, I went with a friend and we walked in and I was like, see you later, I'll be over there. And I just walked away and I was just lost. I have an app on my phone too that I track all the books that I want to read and have read so that I can easily tell which books. I like to read series, so I can tell which books I've already read and which books I need to read next. And as, you know, any good completionist, I have to read them in order, and reading them out of order is a concept that I'm not interested in getting behind. So I've got to make sure that I find all the books, and yeah, used bookstores are a great way to go. So like all those books I bought, our Patreon is only $5 a month for twice as many engineering failures. So those episodes come out on the opposite Sundays from our regular episodes. And on our Patreon feed, we've done a couple different series, which I think are really fun. It's something different that we don't do on our regular feed. We've done a series on amusement park rides, one on environmental disasters, and we have one coming up on the phenomenon known as hydrogen embrittlement, which is more interesting than it sounds. So please go over there and check it out. The money we earn from the Patreon goes to pay for things like hosting fees, web domain, recording equipment, and other things that make this podcast happen.
We are certainly not getting rich off of this podcast by any stretch of the imagination. I mean, we don't even have real advertisers. We wrote all of the ads that you hear. So we do this out of interest and love, and I wanted to be a radio broadcaster, so it's worked out pretty well.
Yeah, I mean, in all fairness, yeah, like Brian said, we're definitely not getting rich off of this podcast. We are, if we break even, it's really exciting for me. So any extra little support you can give us is greatly appreciated. Also, I think we have a little more fun on those episodes. If you could call the regular feed formal, they're a lot more informal. There's a little bit more tangents. We go off topic a little bit more with things that we think are interesting that are kind of, tangentially related to the failure, but maybe not directly related. We kind of have those side discussions, which I think those episodes are a little bit more fun to record, in my opinion. They're also a little bit easier to edit because they're a little bit shorter, which is why we call it the mini failures. Anyways, on to the news this week. We're talking about moving objects with ultrasound waves. And this is along the same vein as the news from last week where we talked about the counterfeit part detection, where they're putting magnetic tags in manufactured products during fabrication. This one's a little bit different, of course, but it still falls into that manufacturing piece, which I thought was interesting. So researchers at the University of Minnesota Twin Cities have developed a new method to move objects with ultrasound waves. That allows the devices to move without needing a built-in power source, which is kind of cool. Using the principles of metamaterial physics, scientists developed a way to move large objects. Whereas before the objects had to be smaller than the wavelength, metamaterials interact with waves like light and sound. And during testing, they placed the object on a table and were able to steer it by sound without touching it, which is kind of like magic, if you ask me.
I mean, as a kid, I tried to fool my brother with a similar thing where I just had a magnet underneath the table and I could move a car around. Not quite the same. This is much more advanced than me with a magnet, but it still sounds super cool. So how it works, there's a specialized pattern that's placed on the object's surface. So with that pattern, they can either push it forward or pull it towards a source, kind of like a tractor beam from Star Trek or Star Wars, or I think Battlestar Galactica had tractor beams as well. Basically, any science show has a tractor beam of some sort. So researchers are planning to test various frequency waves, materials, and object sizes to see if they can refine this a little bit further. The technology has a wide range of applications from manufacturing to robotics by contactlessly actuating things as they move through a process. If you want to learn more about this or read about the study, check out the link on the webpage for this episode at failurology.ca.
This week's episode of Failurology is brought to you by Long's Long Pants.
They're long pants made by Longs.
Not to be confused with shorts. These are different.
This seems pretty self-explanatory from the name.
But yet, here we are, explaining long pants.
Long's long pants.
Now on to this week's engineering failure, the Mount Polley Tailing Dam breach. This one, like the Fernie Arena ammonia leak, is also fairly close to home. Mount Polley is not too far from Calgary. It's, you could drive there in a day. So this one's been on our list for a while, but it's one that I've been a little apprehensive to cover. It is definitely interesting though, so I'm glad that we're doing it today. And I would say that it's more complicated than the typical dam failures that we've covered so far. And it also has a lot more geotechnical components than the dams we've talked about so far. And I know that because there's a lot more dirt words that I had to look up as I was researching this episode. So hopefully I'm pronouncing and explaining those correctly. Sometimes it's interesting. I think about other disciplines as I'm out and about in the world doing my engineering thing. And I think, oh, that would be really interesting. Oh, I wonder what I would be doing if I went into that discipline. But I can say for certain that dirt is not for me.
Oh, I was so close to picking civil engineering as the discipline of engineering that I wanted to study in university. I kept going back and forth between geomatics engineering, which is what I currently practice, and civil engineering, like right up until the last second when we had to make our selections. I have always loved dirt. I loved dirt as a kid. I loved work machines. I thought it would be super cool to be a civil engineer and work on infrastructure projects and dirt works and stuff that had giant machines. So that would have been it was my second choice. If geomatics wasn't a thing, I 100% would have been a civil engineer.
Yeah, I don't know what it is about it. I could talk for a very long time about the different properties and characteristics and performance of different metals, but when we're doing a similar comparison with different types of dirt, it's just not, I don't know. That's how I know what I'm interested in. When it's something that I can't stop thinking about or reading about, I know it's caught my interest. And when it's something that I can't retain, then I know that it's not for me. So anyways, I'm still really glad we're covering this. I do find dam failures really, really interesting. I just don't like to get into the weeds, so to speak, with all the different types of dirt. So anyways, let's move on. If you're a geotech, thank you. You do necessary work. We need you. And I love that you love dirt. It's just not for me. So Mount Polley is a Canadian gold and copper mine located near Williams Lake in British Columbia, BC. The mine is made up of 2 open pit sites and an underground component. It's owned by the Mount Polley Mining Corporation, who is owned by Imperial Metals Corp. The mine opened in 1997 and was placed on care and maintenance, or in other words, closed, in 2019. And it was planned to reopen in 2022, but I didn't find anything that said that had happened. So I believe it's still closed at the moment. The mine material is processed through a mill where the minerals get floated and concentrated, and everything else, known as tailings, is leftover waste material. And the tailings generally consist of crushed rock, water, trace quantities of metals, and additives used in the process, and they're often in the form of a wet slurry. And they get put into these tailing ponds.
So there's 3 types of conventional tailing ponds that are used. They're known as upstream tailing ponds, downstream tailing ponds, and centerline tailing ponds. So just to go through the different types. So upstream tailing ponds, these are where new levels of embankment are built on top of previously deposited tailings, inward from the tailings. And this is a fairly dangerous method as the underlying tailings can liquefy And then they undermine the new embankments, and then your new embankment collapses, and it's bad news bears for everyone. So upstream, not generally a good idea. Downstream tailing ponds, these have new embankments that are built on top of older ones, but the new embankments are built outward from the tailing, so it's a little bit better because it can't really undermine stuff. And then there's centerline tailing ponds, which are built on the center of previous embankments.
And just to add to that, from what I've been able to gather, this is much different than a traditional dam. In a traditional dam scenario, you build the dam retaining wall, and if you did it right the first time, it stays there. And yes, you have to maintain it, but you don't have to change it. Where in this case, the tailings ponds are continually getting larger or deeper. And so you're having to add to the embankment over time as the mine expands and the quantity of tailings or the volume of tailings expands. So that's why we're talking about embankments being built on top of older ones.
So of course, the different types of tailing dams that can be constructed, they depend on a number of factors. So obviously the space, safety of the environment and the workers, and of course the cost. Cost is, no matter what, cost is always a big driving factor in projects. It's been a big driving factor, I think, in almost every project that I've worked on. It seems after the scope is kind of defined, the cost is really the next thing that determines whether the project will go ahead in its current scope or whether there need to be scope refinements done. But either way, the Mount Polley configuration for these tailing dams was known as a modified centerline design, with the core inclined slightly in an upstream direction. 3 adjacent embankments confine the Mount Polley tailing pond on the north, the east, and the south side, with naturally rising ground on the west side. The pond itself was 4 square kilometers in surface area shortly before the breach. The embankments were made up of a core, which acted as an impervious element with a filter zone downstream, and these were supported by a rockfill zone.
Shortly before the breach, the mine had received approval to raise the crest or the embankment of the dam by 2.5 meters. At around 1 a.m. on August 4th, 2014, a breach occurred in the west end of the northern embankment while they were still 1 meter short of the permitted elevation. So they were allowed to raise it by 2.5. They'd done 1.5 at the time when the breach occurred. And the loss of containment was sudden. All of a sudden, the whole embankment just washed out, and most of the tailing pond, if not all of it, left the pond. The tailings, which consisted at the time of 17 million cubic meters of water and 8 million cubic meters of tailing material, carried felled trees, mud, and debris as it wore away the banks of the Haltine Creek on its way to Quesnel Lake. Widespread water restrictions were implemented right away, which, as terrible as that is a good thing that they caught it quickly and they took necessary steps to prevent people from getting sick. But I do want to point out that these weren't boil water advisories because boiling wasn't sufficient. Residents were instructed not to consume the water at all, which meant that they would have had to use bottled water for everything, which is, of course, very annoying, and this shouldn't have happened, but at least they didn't do what they've been doing in Flint since something like 2014, where people drank the water for years before they said something and put in the water restrictions and the boil water advisory, and they still haven't corrected all the issues. If you want to check that out, we covered Flint on a previous episode. I believe it's episode 12, so way back in the day. Initial tests shortly after the breach showed that zinc levels were above chronic exposure limits for aquatic life. A letter of understanding between the province and Soda Creek Indian Band and Williams Lake Indian Band outlines a collaborative approach to jointly address all aspects of the tailings breach. The Ministry of Environment led the response for the environmental monitoring, impact assessment, mitigation, and remediation of the area impacted as a result of this tailings breach. And this work was undertaken with First Nations, local government, provincial and federal agencies, and public representatives.
The agreement has 5 components, and these will be conducted in accordance with First Nations traditions and scientific knowledge, and also recognize the health and safety of the public and workers, including members of the First Nations, are paramount. A principal table consisting of the First Nations and the Ministers of Environment, Aboriginal Relations and Reconciliation, and Energy and Mines will oversee a government-to-government response. A senior officials committee from the 3 ministries and designates for the First Nations will be responsible for overseeing all of the response activities such as assessing impacts, cleanup, remediation planning, and decisions related to future requirements to respond to all aspects of the Mount Polley incident. $200,000 will be paid to each First Nation, so $400,000 in total, to cover the costs already incurred and future costs related to the tailings pond breach. The recognition of the important economic contribution of mining to BC and the commencement of a dialogue about existing laws, regulations, and policies in relation to the mining sector in BC. And lastly, an agreement that the entities responsible pay for all costs and damages incurred in relation to the Mount Polley mine incident in accordance with applicable legislation.
From the beginning of the tailing pond construction in 1995 until early 2011, one company was the engineer of record for the embankments. But that changed responsibility in 2011 and was expected to change again after the 2014 construction season, which creates a really interesting scenario. I think mechanically and probably electrically, it's a little bit easier to come in and make changes to an existing system. I mean, you have to trace everything out, so there's work involved, but it's a little bit easier to figure out exactly what's going on. I always find structural would be a bit unnerving to figure out how you can modify an existing structure without putting it at risk when it wasn't your design in the first place. Structural engineers do it all the time. It just seems a little bit more risky to me. Maybe that's because the structure of a building is more critical, but this embankment is not really any different. You have, a new company coming in and taking over responsibility for a design that wasn't theirs. And now, of course, they're not taking on that liability necessarily, but if they make any changes to a design that they may not fully understand, they're taking liability for any risks that occur. The embankment's elevations had been raised several times since the early 2000s, totaling about a 40-meter increase. The dam embankment was classified as zoned earth and rock-fill dam, and the impervious layer composed of glacial deposits. And so that impervious layer is really just the barrier that prevents the liquid from leaking out. It's meant to be impervious so that it holds back the liquid. But for the most part, the embankments were constructed of earth and rock.
So shortly after the breach, an independent review panel was formed to investigate and determine the cause. Human intervention and overtopping were ruled out as causes, which we've seen in previous dam failures that we've covered. Although we will circle back to the role of water in this failure in a little bit. Piping and cracking, which is where water starts to seep through the embankment layers and erode them from within, was heavily reviewed by the panel. We've talked quite a bit about dams on this podcast, both in our regular episodes that you're listening to right now and also our mini failures that are available on Patreon. Piping and cracking are very common causes of failure of earth dams especially, and the following factors were of concern to the panel. The modified centerline tailings dams, while within precedent, are disposed to longitudinal cracking. Following a previous construction phase, the core width of the dam was reduced to 5 meters, which is really thin for the planned hydraulic head, and again, this has a precedent but requires careful filter and transition design and construction.
And the hydraulic head is the force of all of the liquid and materials inside the dam pushing on the embankment. So that's what we're referring to there.
So hydraulic head is basically, yeah, like Nicole said, the weight of the water pressing down on a surface or on a square on a certain area that's defined. So we see a lot of hydraulic head stuff in pressure calculation. I'm sure Nicole deals with it a lot in HVAC and piping design.
Every day.
I don't deal with it a lot anymore. I used to do some pipeline engineering. I don't do pipeline engineering anymore, but we dealt with hydraulic head quite a bit in pipeline design for obvious reasons, as you're moving gas or liquid through a pipe. So hydraulic head is really important for things like hydro test and figuring out where your compressor stations need to go and other fun things like that. So the filter and transition at the dam were particularly thin and required meticulous care to be constructed as intended. Details of filter and transition construction in as-built drawings indicated departure from the intended design. Much of the as-placed filter material failed to meet applicable filter criteria and requirements for internal stability of its grading. So the core of the dam had been overtopped in one location for a brief period in 2014, resulting in softening and enhanced deformability of the soil. So the core was not contained by the steep rock fill shell in as stiff of a manner as might have been possible, and a cavity was detected in the core remnant of the left abutment of the breach that was the result of internal erosion. Observed flow to the seepage collection system exhibited a transient spike on April 22, 2013, of the kind sometimes characteristic of internal erosion. Despite all these concerns, however, the panel didn't find any evidence that the break was caused by piping or cracking, resulting in uncontrolled internal erosion.
So all that to say that there were issues with the filter, the embankment wasn't built as per design, there was deviations from the design, it had overtopped before, there were cavities forming, and despite all of those things, somehow none of those seem to be the cause of the breach, which is definitely something we've seen before where there's just so many things that could go wrong, and it's something completely different than what you expect that sent it all over the edge. But this kind of seems like a ticking time bomb a little bit to me. I don't know. I guess, to be fair, I don't know how critical each of those items are, but when you see a list that long of potential things that could have caused the failure, it just makes me ask questions. Observations for the surface investigations provided clear evidence for shearing, lateral displacement, and rotation of the embankment that resulted in the breach. And the panel concluded that the August 4th, 2014 breach was caused by shear failure of the dam foundation materials when the loading imposed on them, or the hydraulic head imposed on the embankment, exceeded the embankment's capacity. And because of that, and not surprising, the dam failed rapidly and without really much of a precursor. It just let go. So the shear surface in the remnants of the dam's core and the deformation in the weaker deposited layer of the silt and clay, which is 8 to 10 meters below the original ground surface, supports this failure cause. One of the native soil layers was localized to the breach area, and it went undetected in part because the subsurface investigations that they did before designing this embankment expansion were not tailored to the degree of complexity that they needed to be. And so not only did they not really know that that native soil layer was there to the extent that it was, but they didn't appreciate the lack of strength that it had, or the nature with which it had that performance. And so the problem with this was that as the dam grew higher and the loading increased, this layer's strength behavior would change and it became weaker. And this was not accounted for in the design of the dam. The dam was also unprecedentedly steep. And while this was justified by the design analysis, it was unreasonable in practice. And honestly, I see this all the time. Things look great on paper. Things can look absolutely fantastic on paper, and they just don't work in real life. And you really do have to think about how people are going to construct things when you design them. That's a really, really important part of design. And that's why, journeyman trades are so important, because they're professional contractors just like we're professional engineers. And they know much more about how to put things together in real life than I do. And so I need them to tell me when stuff's not going to work so I have an opportunity to fix it. There was another area of the embankment that also had similar characteristics. It was also just as steep, but it was additionally supported by a buttress, and so therefore it didn't fail. So that other steep section had an extra level of support that this breach section just did not. Other contributing factors to the breach include the dam's raising methods were evaluated a year at a time, and they were bordering on an ad hoc method rather than planning in advance. So rather than looking at where the mine would be in the next 3 years, 5 years, 10 years, and designing embankment expansions for a longer term, they were just raising it year after year as the needs of the dam changed, which I get from a financial perspective, but I think in the long run, you're probably spending more money and your designs are more precarious because you're not able to really put in that good support. You're just adding a little bit at a time. And so maybe you're not doing a full thorough review like you would be if you were adding a large section to the embankment all at once. There was instrumentation in place around the embankment of the dam, and that was relied upon as a substitute for other input parameters and design projections. But for both practical and strategic reasons, the dam was ill-suited to this approach. So the steep slopes and constant construction prevented installation of the instruments at optimal locations, which makes sense. If they're hard to get to, or they won't work properly, or you're just going to move them in 6 months when you do more construction, those instruments never get put where they need to be. And therefore, you're trusting readings that aren't really giving you an accurate representation of the true integrity of the dam wall. As well, the instrumentation program was incapable of detecting critical conditions because the strength behaviors were not recognized. So because they misinterpreted or didn't fully appreciate that native soil layer that was becoming weaker as the dam wall got taller and taller, they weren't actually able to look out for potential causes of failure of that layer. So it's almost like that whole piece went undetected throughout design and construction. And so they had, this really weak link in the chain that they almost didn't know about. And so they weren't able to strategically place sensors around it to watch for any sort of cracks in its integrity. Back to the water, while the dam didn't overtop, water did play a part in the failure. There were high water levels at the time of the breach, which had some influence on the dam stability, as well as the high water required less of a drop in dam crest before overtopping occurred, which would have possibly allowed some time for intervention. And what I mean by that is that if the water level was fairly low and there was a breach, you wouldn't lose as much water. But if only a small drop in the embankment wall is required to get to the water level, once it does start to overtop, it just erodes that entire embankment until the tailings pond or the dam is pretty much empty. Water is a very, very powerful thing. If the water level was lower, it also would have reduced the amount of sediment and water erosion downstream. The panel found that the regulator and inspections were within reason and didn't contribute to the failure, suggesting that since the flaw in the foundation design was unknown, it was unpredictable. And I mean, to an extent, I agree with that. If it's unknown and there's no possible way that it could be known to the installers and the inspectors, the regulators, their role is to follow the design drawings. And now if there was an obvious flaw in the design drawings that everyone could see and they didn't question it, that's one thing. And I think at that point you'd find some fault in them not waving the white flag. But this is outside of my expertise, so I'm just speculating based on the research that we've done and the report that we read. But it does seem like due to a lack of investigation and testing prior to completing the design, a lot of the flaws were unknown to the naked eye. And so it really does fall back onto the geotechs and the engineers to have discovered that information during their design process, which is, it's hard. I never want to speak badly about another engineer. And that's not what I'm trying to do here. But I don't think any of the engineers involved in this failure woke up one morning and were like, yeah, we're going to design a dam that's going to fail. I mean, most people don't wake up with that intention, but unfortunately that's still what happened here, and that sucks.
Yeah, I mean, very similar, kind of in that same vein. When you drive to work or you commute to work, whether it's walking or by bicycle or you transit, however you get to work, nobody hops in their mode of transportation and is expecting or is looking forward to or intending to get in an accident of some sort that day. And unfortunately there are incidents and accidents that do happen every day for various reasons that do directly and indirectly impact all those people involved. But yeah, just to echo Nicole's point, nobody wakes up in the morning wanting something horrible to happen to them professionally or personally. So the outcome of all of this, the engineers and geoscientists of British Columbia, or EGBC, conducted a number of disciplinary proceedings, and they concluded their disciplinary proceedings in 2022.
And EGBC is the regulating body for engineers and geotechnologists and scientists within the province of British Columbia, which is the same as a PEGA for Alberta or a PEGAS in Saskatchewan or
GEO for Ontario. I can't remember what the Yukon one is, but yeah, every province or territory has a regulating body for engineers, and most of the time geoscientists as well, and geophysicists. Sometimes they're in a separate body. But here in Canada, every province or territory has some sort of regulatory oversight body that if you want to practice engineering or, in some cases, geoscience stuff, you have to be a part of the regulating body. Not anyone can just call themselves an engineer or a geoscientist or a geophysicist. So in Canada, those are all protected terms. In the States, there's, I believe anyone can call themselves an engineer, so you don't have to go to an accredited school. You don't have to, kind of serve a period of 4 years of professional development time. So here in Canada, it's a lot more regulated, on that side of things.
If you want to hear more about that, we did an episode, I think it came out just before Christmas, episode 65, which talks about the time that Quebec's engineering regulating body lost their ability to self-regulate, which was really interesting to research and talk about. But in that episode, we also talked about the history of engineering in Canada, some of the major differences between Canada and the United States, also the history of engineering in Alberta specifically, since that's where Brian and I both practice. And then, of course, we talked about the issues that happen in Quebec. So if you want a little bit more background on engineering as a profession, check out episode 65.
As a result of the disciplinary proceedings, a senior geotechnical engineer was fined $25,000 and paid $69,000 in legal fees for their part in the breach. They ceased practicing engineering in 2018 and resigned their license in 2020. So the engineer of record for this project, who at the time was a junior engineer, they had their license suspended for 2 months and had to complete 3 education courses related to tailings management, tailings facility design and operation, and engineering management for mine geo-waste facilities. The engineer of record's boss was fined $25,000 and paid $107,500 in legal fees for not adequately supervising a junior engineer and not properly fulfilling the role of review engineer. This person resigned their engineering license in 2018.
I just want to mention that I think it's interesting and telling here, and something important to note, that 3 engineers were found responsible and held liable to some extent through fines and other things for the breach that occurred at the Mount Polley Tailings Pond. And I think there's this thought that one person is responsible, but there are many people who have their hands in the cookie jar, so to speak. And, there are multiple steps and layers to this process, including there's the person who's doing the design, but they're not necessarily doing every single aspect of the design. They may be just overseeing it, or there's usually people who are doing the drafting or the drawings, the blueprints that go along with it. And then there's someone doing peer reviews and overseeing the work. And then in this case, you've got, geotechnical and civil engineers working together to complete the design. And so that's something to keep in mind, because I think that a lot of engineers I've come across, and especially people who are newly licensed, think that if they don't stamp something, they're not liable for issues that may occur as a result of that design. And that's just not the case. If you're a professional engineer and you are registered, then you can be held liable if there is an issue with that design. And so I think that's something that's really important for people to keep in mind when you are a practicing engineer, whether you're stamping or not. Don't put it on paper if it's not been properly designed.
And remember, if it's also out of your scope of practice or you're not comfortable with it, there's zero issue, or at least I have zero issue with people wanting to ask somebody that's more of a subject matter expert or knows more about this area than what they do. Even though it's kind of similar to this in the law profession, even though we're all engineers, we all have different areas of specialization. I literally could not do Nicole's job because I have no idea how HVAC and ducting and pumps, I have no idea how that works. I've never taken a course on it. So I can't practice that kind of engineering. Some of the engineering work that I do, Nicole literally has no idea how the magic in my engineering side of things works. So everyone's got their own specialization and their own area of interest. And even within an engineering discipline like mechanical engineering or civil engineering, the longer that you practice in that discipline, I feel like the more and more specialized you get in certain areas. Nicole spends a lot of time doing, HVAC and piping design within mechanical engineering, but then there's other mechanical engineers that are doing, car design, or they're designing other things that Nicole would literally have no clue about how to do just because that's not her area of practice.
For sure, for sure. I think there's sometimes a perception of people who aren't in the engineering world that because you're an engineer or, like Brian mentioned, a lawyer, you know everything about that field, but that's just not the case. And it's perfectly fine to put your hand up and ask a question. It makes us all better, and it makes us all work together better as well. We have that privilege, because it is a privilege, not a right. We have the privilege to self-regulate our profession because we are held to a high ethical standard to determine for ourselves what we can and cannot do as engineers, where we are formally trained and where we're not. And if people just started stamping whatever they wanted, regardless of their training, we would lose that right to self-regulate, and that would be really unfortunate.
So there you have it, the Mount Polley Tailing Pond breach. An undetected soil layer and inexperienced design choices led to a breach of the tailings pond in August 2014 and serious consequences for 3 licensed professionals.
For photos, sources, and an episode summary from this week's episode, head to failureology.ca. If you're enjoying what you're hearing, please rate, review, and subscribe to Failureology so more people can find us. If you want to chat with us, our Twitter handle is @Failureology. You can email us at thefailureologypodcast@gmail.com. You can connect with us on LinkedIn, or you can message us on our Patreon page. Check out the show notes for links to all of these. And thanks everyone for listening. Tune into the next episode where we'll talk about the 2021 Texas power outage. Bye everyone. Talk soon.